Okay, hi. So I'm going to be talking about methane as a greenhouse gas for my presentation and how it contributes to climate change. So I'm going to start by talking about greenhouse gases and how they increase atmospheric temperature. So first, radiation from the sun is absorbed by the Earth and then re-emitted into the atmosphere as infrared radiation. Then greenhouse gas molecules absorb this infrared radiation that comes from the sun, which then leads to the greenhouse effect, which is when Earth's surface is warmed by the sun and some of the heat is trapped by the greenhouse gases in the atmosphere. The greenhouse effect has caused the temperature of the Earth's atmosphere to begin to be increasing since the Industrial Revolution, which gave rise to an increase in the concentration of greenhouse gases in the atmosphere. Currently, the atmosphere is composed of almost 80% N2, about 20% O2, 0.037% CO2, and 0.00017% methane. So, as I stated, greenhouse gases absorb infrared light from the sun. It is this absorption of photons that leads to higher kinetic energy within the vibrations of the molecules. This is due to the fact that an increase in the concentration of greenhouse gas molecules in the atmosphere leads to increased absorption of light from the molecules. Increased absorption of light causes an increase in the vibrational motion of the molecules. The increase in vibrational motion leads to an increase in kinetic energy within the vibrations of the molecule, which then causes an increase in temperature, and temperature is a measure of average kinetic energy of a gas. So that's how kinetic energy and temperature are related. Furthermore, the increased kinetic energy from the greenhouse gas molecules can be transmitted to molecules in the atmosphere that are not greenhouse gases, such as N2 and O2, which also contributes to the warming of the atmosphere and climate change. In addition to this, Beer's law can be used to show how greenhouse gases are contributing to climate change. Beer's law states that absorbance is equal to the molar extinction coefficient times the path length times concentration. From the increase in atmospheric temperature, we know that the amount of light that is getting absorbed has increased. From Beer's law, we know that the concentration of methane and other greenhouse gases in the atmosphere has increased as well. And we know this because we still have the same amount of infrared light coming from the sun, but there's more of it being absorbed. Therefore, we know that the concentration is increasing since absorbance and concentration are directly correlated according to Beer's law. Next, I'm going to be talking about the specific greenhouse gas methane and then later comparing it to carbon dioxide. So the harmonic oscillator model describes the vibrational motion of a molecule, which, as I have explained, plays a large role in describing how greenhouse gases contribute to climate change. So I'll be using this model to describe the vibrational motion of methane. So non-linear molecules have different vibrational motion than linear molecules, and since methane is a non-linear molecule, it will have 3n minus 6 vibrations, where n is the number of atoms, which is 5. So that gives us 3 times 5 minus 6 equals 9 total vibrations. These include stretching vibrations, which is when the bond oscillates between the nuclei of the atoms being too far apart and too close together. Bending vibration occurs as the atoms oscillate between different angles of energy. All molecules have 3 types of vibrational motion. First, there's a symmetric stretch, which would involve the hydrogen stretching and compressing away from the carbon simultaneously. However, the symmetric stretches are not seen on the infrared spectrum. Second, there is the asymmetric stretch, which is the highest in energy. This consists of asymmetric movements of the atoms, such as some hydrogens compressing while others are stretching. Asymmetric stretching is responsible for the IR peaks we see in methane and CO2. Lastly, there are bends, which are much lower in energy and show up around the 300 to 400 wave number range. Bending involves the hydrogens moving towards and away from each other. So in summary, the asymmetric stretches of methane are the most important when discussing climate change. Next, I'm going to talk about how selection rules apply to the absorption of infrared light. So selection rule number 1 states that for light to be absorbed, a change in dipole moment must take place. Um, Methane has no net dipole moment because of symmetry, but it can still have a change in dipole moment due to the asymmetric stretch. So even though methane has no net dipole moment, we can still see an IR spectrum because certain motions involving the asymmetric stretch have a dipole moment that changes from the original molecule and thus creates an IR peak. So as we will see later, methane has an IR peak at 1300 wave numbers that represents the asymmetric stretching of the molecule. Next, we have the harmonic oscillator model equations. So these are equations for diatomic molecules, so they don't directly apply to methane since it's not a diatomic molecule. However, we can still use them to approximate the energy of the stretches within non-diatomic molecules like methane because they use similar types of equations. So we have the energy equation, the equation for frequency of vibration, and the transition dipole moment formula, which tells us whether the transition will show up on the IR spectra or not. So the main flaw of the harmonic oscillator model is that it allows bonds to be compressed or extended to infinity, which implies that bonds are unbreakable, which we know is not the case. So the anharmonic oscillator model corrects for the fact that bonds can't stretch to infinity because it allows you to calculate the dissociation energy of the molecule, which is the amount of energy required to break the bond. The anharmonic oscillator energy equation and dissociation energy equation are shown here. Again, these equations apply to diatomic molecules, but they still correct for the fact that the bonds can break within the molecule of methane, and for the fact that the asymmetric stretch is not going to be equal for each energy level. Now I'm going to compare methane and carbon dioxide as greenhouse gases. So it actually turns out that methane is a more powerful greenhouse gas than CO2, even though the concentration of methane is lower in the atmosphere. This phenomenon is due to the band saturation effect, which ultimately explains that the more abundant the greenhouse gas, the less powerful each molecule is at absorbing infrared light. So there are more CO2 molecules in the atmosphere, and the CO2 molecules that are higher in the atmosphere filter the light as it enters. So by the time it reaches the lower CO2 molecules, there's less light to absorb. With methane, there are less molecules at the higher altitudes, so the light does not get filtered as much, and the methane molecules are able to absorb more infrared light. Therefore, methane is a more powerful greenhouse gas than CO2, even though there is less of it in the atmosphere. This is similar to if you shine a flashlight through a murky liquid. If you have a smaller amount of the murky liquid, which represents methane, more light will get through. But if you have a larger amount of the murky liquid, which represents CO2, less light will get through. And that explains why more light is able to be absorbed for methane. Lastly, I'm going to discuss the IR spectra of carbon dioxide and methane, which are both shown here. The methane IR spectra has significant peaks at 3000 and 1300 wave numbers, and that's the wavelength at which methane absorbs infrared light, which is different than CO2, which has peaks at 3600, 2300, and 700 wave numbers, which again represents the wavelengths at which CO2 absorbs infrared light. So the fact that CO2 and methane absorb light at different wavelengths actually contributes to climate change even more because they're able to absorb more light, which causes an increase in kinetic energy within the molecular vibrations and therefore an increase in temperature. Um, so if methane and CO2 absorb light at the same wavelength, they'd be competing to absorb the light, so there would actually be less total light absorbed. But since they absorb light at different wavelengths, they're not competing to absorb the same wavelength. So combined, they're able to absorb more light, which causes a higher increase in kinetic energy and a larger impact on climate change. So in conclusion, the harmonic oscillator model can be used to describe the vibrational motion of methane, which can be used to explain how methane causes an increase in atmospheric temperature. The IR spectra of methane and CO2 can be used to show the relationship between the two greenhouse gases and the difference in their contributions to climate change. Thanks for watching. Here are my sources.